Okay, so let's get into an example. All right, switching over to the tablet. All right, here we go. Starting with y equals pi to the power t. Notice that this is an exponential function. The variable is in the exponent. So we're going to use the formula that we were just looking at for the derivative of a general exponential function. This would be dy dt is equal to pi to the t times natural log pi. And that's it. All right, now here's a thing I like to do. So that example was y equals pi to the t. The next example is y equals t to the pi. Why don't you think about this one for a second? Pause the video if you are so inclined and think about what would the difference be between this one and the last one. Well, the difference is that this is not an exponential function. This is technically not a polynomial, because with a polynomial, the exponents have to be integers, but it differentiates like a polynomial. It's almost a Calc 1 problem, except in Calc 1, we didn't talk about exponents being pi. The worst they could be was fractions. But on this one, you just use the power rule. So this one would just be pi times t to the power pi minus 1. So very different from letter A, right? Okay. And then we have this one, y equals 5 to the power negative cosine 2t. So I'm going to take my time with this one because I believe this is a chain rule within a chain rule. So dy dt is going to be 5 to the power negative cosine 2t times natural log 5. And now we have to multiply by the derivative of negative cosine 2t, right? Okay, so 5 to the power negative cosine 2t times natural log 5. Okay, so what is the derivative of negative cosine 2t? Well, it would be negative, and then the derivative of cosine is negative sine, so there's another negative. This is going to be negative sine 2t times the derivative of 2t, which is 2. All right, so putting it all together, we have I kind of want to put this 2 sine 2t in front, maybe. It would be 2 sine 2t times 5 to the power negative cosine 2t times the natural log of 5. All right, that was fun. Okay, let's see. And then we had a couple of integral problems, right? Starting with this one, the integral of 3 to the x over 3 minus 3 to the x dx. So this is a substitution. We're going to let u equal 3 minus 3x, 3 to the x. And then du would be the derivative of 3 minus 3 to the x. So the 3 will disappear. We'll have the minus sign. It'll be negative 3x, 3 to the x times natural log 3 dx. Okay, but what do we actually want? We don't want the natural log 3, and we don't want the negative sign. So why don't we divide both sides of this equation by negative natural log 3. And that's going to give us negative 1 over natural log 3 du is equal to 3 to the x dx. All right, and now I think we're in business. So we're going to replace our 3 minus 3 to the x with u. And then we're going to replace 3 to the x dx with du, but we're going to stick here a minus 1 over natural log 3. So hopefully you remember this integration formula. The integral of du over u is natural log absolute value u plus c. All right, so putting it all together, we're going to have negative natural log absolute value 3 minus 3 to the x over natural log 3 plus c. Okay. And let's see, was there one more integration problem? Yes, there was. All right, the definite integral from 0 to pi over 4 of 1/3 to the power tangent t times secant squared t dt. So this is another substitution. Again, substitution is basically the only integration trick that we know. That's about to change when we get to chapter 8. Okay, I'll never forget years and years ago, I was teaching Calc 2 and started right in with the substitution, and I had a student get very wide-eyed and say, I'm supposed to remember substitution? I thought we were done with that already. And I kind of laughed and they said, you're never going to be done with substitution. All right. Okay, so this time, and remember with substitution, you're looking for a function and something that looks like its derivative. So in this case, u is going to be tangent t, and then du will be secant squared t dt. And why don't we change our limits of integration? You know I like to do that. X goes from 0 to pi over 4. Whoops, it's not x, is it? It's t. Okay. T goes from 0 to pi over 4. And u is equal to tangent t. So the lower limit is going to be tangent 0, which is 0. And the upper limit is going to be tangent pi over 4, which is 1. So the new and improved integral is going to go from 0 to 1, and it's going to be 1/3 to the power u du. All right. So how did that integration formula go? It said that the integral of a to the u was a to the u divided by the natural log of a. And we should be able to pretty this up a little bit. So now we're going to plug in 1, plug in 0. Why don't we park this 1 over natural log 1/3 outside? And then inside, we're going to have 1/3 to the power 1 minus 1/3 to the power 0. So inside the parentheses, you have 1/3 minus 1, which is negative 2/3. And then remember that natural log 1/3 is equal to the opposite of natural log 3. This isn't going to be quite as pretty as I thought it would. 1/3 minus 1 is negative 2/3. I almost have room to write the answer, but not, well, maybe if I squeeze it down here. Okay, so my final answer would be 2 over 3. Okay, I give up. Gonna have to write the answer somewhere else. Okay, natural log 3. Almost had room for it, just not quite. I'm gonna write the answer up here. Okay, so it would just be 2 over 3 natural log 3. I think that's just about as pretty as I can make it. All right, back to the presentation. Okay, so the last thing we have to talk about is logarithms with base A. Of course, logarithm with base A is the inverse of A to the X. And so if I wanted to prove these formulas that I'm about to show you, that's how I would do it. I did it once already with e to the x. I defined e to the x to be the inverse of natural log x, and then I used what I knew about natural log x. So we'll just say if you wanted to do that, you could. I will spare you those details. So again, for any positive number a not equal to 1, log base a of x is the inverse function of a to the x. And you have these inverse properties for a to the x and log base a of x. A to the power log base a of x is equal to x for all x greater than 0, because that's the domain of the logarithm. Log base a of a to the x is just x, and that's good for all real numbers x. Remember your change of base formula from pre-calc? Log base a of x is equal to natural log x divided by natural log a. This is actually the easiest way to do anything in terms of a general logarithm, would be to write it in terms of natural log x. That would actually get you out of ever having to use the formulas that I'm about to show you. Not these ones here, but the derivative and the integral. Okay. Notice that your product rule, quotient rule, reciprocal rule, and power rule all apply for your general logarithms, and I think I will be using those at some point. Okay, here it is. So the derivative with respect to x of log base a of u is equal to 1 over natural log a times 1 over u times du dx. So it looks just like the derivative of natural log u, except that this factor 1 over natural log a pops out. And again, if you write log base a of x using the change of base formula, it's very easy to understand why this rule is correct. Okay, so let's look at these examples. And actually, I guess I never showed you an integration formula for log base a of u. And so you know what I think I'm going to do? I think when I go to evaluate this integral, I will use that change of base formula. All right, so back to the tablet, and then we'll be done with this section. All right, here we go. So in this problem, we are looking for dy dx. So using the formula that we were just looking at, that would be 1 over natural log 25 times 1 over u times du dx. So something kind of cool happens in this case, because du dx is equal to e to the x. So we'll deal with that in a second, but that's kind of nice. And it's interesting to think about, why does that happen, right? And I think if you rewrite your log base 25 of e to the x using the change of base formula, you'll see exactly why that happens. All right, so let's look at this. Okay, so this is going to be 1 over natural log 5 times 1 over u, which is 1 over the square root of x, times the derivative of square root of x, which is 1/2 x to the negative 1/2, right? Oh, I have a feeling something exciting might happen with this problem. Okay, so of course here the e to the x's drop out, so all we're left with here is 1 over natural log 25. And then let's look at what happens over here. So we have a 1 over the square root of x, and then 1/2 times x to the negative 1/2 is just 1 over 2 square root of x, isn't it? All right, so that's going to be 1 over natural log 25 minus 1 over 2x times natural log 5. All right, now if we really wanted to, we could write natural log 25 in terms of natural log 5, right? Because 25 is 5 squared. And then we could use our power property of logarithms. Really no point in doing that. I'm just going to leave it like this because this x here, which I don't have in the other term, is going to prevent me from combining those two terms in any way that's going to be super pretty. So I'm just going to leave it like this. It's a reasonably pretty answer. All right, next. Doesn't this look fun? Well, actually, we're going to be able to make this a lot easier. So y equals log base 5 of the square root of 7x over 3x plus 2 to the power natural log 5. So before I do any calculus with this, let's break that down using properties of logarithms. So first of all, square root is 1/2 power. So why don't we write this as log base 5 of 7x over 3x plus 2. And then we can just make this exponent 1/2 natural log 5. Then we can use our power property and go and put that out front. So now we have y equals 1/2 natural log 5, remember that's a constant, times log base 5 of 7x over 3x plus 2. And then finally, we can use the quotient property to write that log base 5 as log base 5 of 7x minus log base 5 of 3x plus 2. That's going to be a lot easier to differentiate than if I had tried to do it the way they gave it to us. Okay, so now we're ready for dy dx. This 1/2 natural log 5, you can just leave that there because it is a constant multiple. Okay, and then the derivative of log base 5 of 7x, that would be 1 over natural log 5 times 1 over u, which would be 1 over 7x, times du dx, which would be 7, right? Minus 1 over natural log 5 times 1 over 3x plus 2 times the derivative of 3x plus 2, which is just 3. All right, so now look what we can do. We can take this natural log 5 and distribute it so that it knocks out that and that. This is the kind of thing I would never dream of doing in a Math C class, but I think you all can handle it. All right. while we're at it, we can get rid of these 7s, but we cannot get rid of the 3s, unfortunately, right? So we are left with 1/2 times 1 over x minus 3 over 3x plus 2. And that's exactly how I would write it. All right, on to the very last example. It's an integration problem. And again, I did not show you a formula for the integral of log base a of u du. So to get out of having to show you a formula for that, I'm going to use the change of base formula. Okay. So let's write this as integral from 2 to 3 of 2 times. And now instead of writing log base 2 of x minus 1, I'm going to write natural log x minus 1 over natural log 2. And then here's x minus 1. All right. So now if we wanted to, we could pull that 2 over natural log 2 out front. Why not? Makes it look a little nicer. So then we're just left with natural log x minus 1 over x minus 1. All right. So how are we going to evaluate this integral? Well, trying to remember if we've done one like this before. Believe it or not, it is a substitution. Well, of course, it's got to be, right? But sometimes the trick with substitution is, what do you make u? Well, in this case, u is going to be natural log x minus 1. And why is that a good thing to do? Because then du is going to be 1 over x minus 1 dx. Look, that's exactly what we need. So we'll have u and we'll have the du. And then what will the new limits of integration be? Okay, this time the old one was x. X was going from 2 to 3. U is natural log of x minus 1. So the new lower limit will be natural log of 2 minus 1, which is natural log 1, which is 0. And the new upper limit will be natural log of 3 minus 1, which is natural log 2. So our new and greatly improved integral is going to be, so we'll leave this constant outside. It's going to go from 0 to natural log 2, and believe it or not, it's just going to be u du. Isn't that cute? What is the integral of u du? Well, that's backwards power rule, right? That's u squared over 2. Plug in natural log 2, plug in 0. We can get rid of these 2's. So we're going to have 1 over natural log 2, and then we're going to have a natural log 2 squared minus 0. And we can do this natural log 2 with one of these natural log 2's, and the final answer just comes out to be natural log 2. Isn't that nice? All right, so that's going to do it for section 7.3. We'll see you next time.